Okay, section 14.5 is our final section of chapter 14, and it's a pretty important section. So this is about the binomial theorem. There are 4 things to do in this section. Number 1 is we're going to take a look at Pascal's triangle, which you may or may not have learned before. And then after Pascal's triangle, we're going to take a look at factorials. And then we'll see the binomial theorem put together. So the reason I say this section is important is because this is something that we continue to teach students all the way through some of the higher levels of math. So you learn it first here in this class, and then if you go on to college algebra, you'll see it again in that class. If you go on to pre-calculus, you'll see it again in that class. We teach this all the way up into a class called discrete mathematics. This is just a really important theorem in math, and it's all based on how to expand binomials. But we're going to take it step by step, piece by piece. So let's start with Pascal's triangle. So Pascal's triangle isn't really a triangle, and if you know what this is, you'll know what I mean. But it looks like this. So it starts with a 1, and then it's a 1 and a 1 out here. And then it's a 1, a 2, and a 1. And then a 1, a 3, and a 1. And then a 1, a 4, a 6, a 4, a 1. So you can hopefully see the pattern that's happening. To get the terms inside, you add the 2 terms that would make an upside down triangle with it. So 1 plus 2 equals 3, 2 plus 1 equals 3. And then the outside numbers are always 1s up and down. So the next row would be 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then a 1 to finish out the row. And this continues on forever. So Pascal's triangle, not really a triangle, it's an infinite set of expansions. And what this expansion is for expansions of binomials, a plus b. This first row represents a plus b to the 0. Everything to the 0 equals 1. The second row is a plus b to the first. Now, you might be saying, well, a plus b is not equal to 1 and 1. And what these are coefficients. So what this says is the coefficients on A and B are 1 and 1. It's a pattern. So this row down here is a plus b to the 4th. So we're not saying that it equals 1, 4, 6, 4, 1. We're saying that the coefficients follow this pattern, 1, 4, 6, 4, 1. So let's look at an example. So we're going to expand. Expand the following. And we'll do x plus 2 to the 4th. So we'll do this the old-fashioned way, and then when we get to the binomial theorem, we'll come back and try this again. So expanding this, we know that this is x plus 2 squared times x plus 2 squared. And x plus 2 squared is x squared plus 2x, or plus 4x plus 4, times x squared plus 4x plus 4. So let's just take a look here. The pattern for our perfect square trinomial is always a squared plus 2ab. A plus b squared is always a squared plus 2ab plus b squared. And so the coefficients here are 1 times a squared, 2 times a times b, plus 1 times b squared. Notice that that follows our Pascal's triangle, 1 times a squared, 2 times ab, 1 times b squared. So we need to expand this out here. So this is going to be x to the fourth plus 4x cubed plus 4x squared. Distributing that one, now distributing the 4x, we're going to have plus 4x cubed plus 16x squared plus 16x. And then finally we'll distribute the 4 plus 4x squared plus 16x plus 16. So this is x to the fourth plus 8x cubed. And then there's 4, 8, and 16 is 24 x squareds, if I'm not mistaken. And then the x's, there are 32. And then plus 16. So if you're trying to figure out, well, how does this match this pattern? Well, the idea is that this is 1 times x to the fourth plus 4 times 2x cubed plus 6 times 4x squared plus 4 times 8x plus 1 times 16. And there is where our pattern comes into play. So what the binomial theorem does is say, let's combine Pascal's triangle along with how to figure out what these numbers should be and what these terms should be. So the pattern that we have in Pascal's triangle is only half of the picture we need. It only gives us this pattern that showed up here. It doesn't tell us what these terms should be. And that's what the point of the binomial theorem is all about, is to show those specific things. So to take a look at the binomial theorem, we need to take a look at a mathematical operation or a mathematical construct called factorials. So factorials are given by the exclamation mark symbol. So this is read as n factorial. Now n has to be greater than or equal to 0. We don't do factorials for negatives. And it's because of the way that factorials are defined. And n factorial is n times n minus 1 times n minus 2. And this continues until we get down to 3 times 2 times 1. So whatever number you're at, whatever integer you're at, you just multiply all of the integers up to 1 that came before it. Now there is one very special factorial, and that's the 0 factorial. This equals 1. And the reason for this is very simple. It's the fact that factorial comes from a branch of mathematics called combinatorics, which is all about counting stuff. Now, factorials is a special type of counting where you count up everything you have and then you multiply everything you have. So you're counting up the number of integers you have up to n, and then you're multiplying all of those. Well, when we're counting integers here, 0 is still an integer, so we still have one number there. And it still, therefore, gets counted, but there's no multiplication. It's the same reason why 1 factorial equals 1, because there's no multiplications happening there. It's just 1 times, well, nothing. There's nothing to put next because there's no other numbers less than 1. So 1 times 1. 0 factorial is equal to 1 because of this same type of reasoning. There's a special reason why 0 factorial equals 1, but it's outside the scope of our class and we don't need to know. All you need to know is that 0 factorial is equal to 1. So let's take a look at some examples just to kind of get the factorials straight. So you should try these on your own because you have the formula here. And it's just getting practice seeing factorials and evaluating them. So we're going to do 3. We're going to do 6 factorial. We're going to do 5 factorial over 6 factorial. And then we're going to do 10 factorial over 7 factorial times 3 factorial. So at the very minimum, try out part A on your own. But I'm going to start going through these. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Now, memorizing factorials is something some people do. I would not recommend you memorize any factorials higher than 5 factorial. And the reason for that is once you get to 5, you're just multiplying more. So you're really just memorizing big multiplications. Now, these are easy here. 1 times 2 is 2, 2 times 3 is 6, 6 times 4 is 24, 24 times 5, that's where it starts to get a little hazy, and I memorized that that's 120. So this is 6 times 5 factorial is another way to write this, or 6 times 120, which gives me 720. So I wouldn't memorize past 5 factorial because there's no real need to. You just multiply the numbers after that. If you have 8 factorial, well, you get to 5 factorial, you know is 120 times 6 times 7 times 8. And that's how I would handle that. So 6 factorial is 720. Now, moving on here, when we're dividing factorials, the goal is always to eliminate the largest factorial that we can. So we're going to expand the bottom and not the top into 6 times 5 factorial, because that's what it is here, and that's what we showed in this last one. This entire 5 factorial can get canceled, and we're just left with 1/6. So when we are canceling and dividing factorials, you don't want to multiply it out and then divide. You want to try and cancel the largest factorial from the numerator that you can first. So that takes us to part C now. When we look at this, we know that 10 factorial is 10 times 9 times 8 times 7, blah, blah, blah. Since I already have a 7 factorial, we know that a 7 factorial lives inside of 10 factorial. It has to, by the way it's defined, the way factorial is defined. So I'm going to expand 10 factorial into 10 times 9 times 8 times 7 factorial over 7 factorial times 3 factorial. Now I can cancel the whole 7 factorial. Once the largest factorial is gone, you need to expand this factorial into what it is. 10 times 9 times 8 times nothing over 3 times 2 times 1. And now you just cancel. So 3 goes into 9 3 times, 2 goes into 8 4 times. So this is 10 times 12, or this is equal to 120. So this is the way we want to try and evaluate factorials, by canceling the largest one we have. And the reason that I show you this is because the binomial theorem is built on factorials. So I said a few minutes ago that it connects Pascal's triangle and gives us the other half of that expansion. So to expand a plus b to the n, where n is greater than 0 and an integer, we have the following. I would not recommend you try and squeeze this in if you don't have enough sheets. It is quite long. I mean, I say quite long, but it's long. I'm going to use the whole length of the page here. So a plus b to the n equals 1 times a to the n times b to the 0 plus n over 1 factorial a to the n minus 1 b to the first plus n times n minus 1 over 2 factorial times a to the n minus 2 b to the second. And we'll do one more term here, plus n times n minus 1 times n minus 2 over 3 factorial. I do not have enough space. Let me write that down here. So this was n times n minus 1 times n minus 2 over 3 factorial times a to the n minus 3 times b to the third. And then this continues, plus dot, 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 all the way to n factorial over n factorial, a to the 0, b to the n. So I know it looks a little confusing. I just didn't want to squeeze anything in here. But essentially, you start with 0 factorial over 0 factorial, if we wanted to write it that way. But it looks funny, so we usually just do 1. And then it's a to the nth power times b to no power, 0. So that's going to go away. Then we start the factorial, I like to call it the factorial climb, starting at n and 1 factorial. Then it's a to the n minus 1, because we have 1 factorial here, and b to the first. Now notice, n minus 1 plus 1 gets back to n. Keep that in mind as we go through these terms. So now we climb the n up 1 towards n factorial, n times n minus 1. We up the factorial on the bottom to 2, and now we have n minus 2, a to the n minus 2 times b to the 2. Notice again, n minus 2 plus 2 gets us back to n. The third term, we climb one more term towards n factorial, n times n minus 1 times n minus 2, over 3 factorial, upping that number. Then it's a to the n minus 3, because there's a 3 factorial, times b to the third. Once again, n minus 3 plus 3 gets us back to n. This pattern continues until you finally complete the factorial in the top, going smaller and smaller numbers being multiplied again and again. And then your bottom term will be n factorial. Then you'll have n minus n, or 0, and b to the n. Again, 0 plus n gets us back to n. So all of your exponents for your two numbers inside the parentheses, when you add those exponents up, you should get to this power. So let's go back to that first example we did. And expand x plus 2 to the fourth. Now we're going to use the binomial theorem. So our theorem says our a is x, our b is 2, our n is 4 from this formula. So this equals 1 times x to the fourth times 2 to the 0. Then it's plus 4 over 1 factorial x to the 4 minus 1 times 2 to the first. Then it's 4 times 3 over 2 factorial x to the 4 minus 2 times 2 to the second. Then it's 4 times 3 times 2 over 3 factorial times x to the 4 minus 3 times 2 to the third. And then it's 4 times 3 times 2 times 1, 4 factorial, over 4 factorial, times x to the 4 minus 4 times 2 to the fourth. So simplifying each term, this becomes x to the fourth. 1 factorial is 1, so this is just 4 x cubed times 2. and then plus, this is 12. 2 factorial is 2. So this is 12 over 2 is 6. X to the second times 4. 4 times 3 times 2. 3 factorial is 6. So there's a 6 here, and here's a 6. So this is just 4. X to the 4 minus 3 is 1. 2 cubed is 8. And then 4 times 3 times 2 times 1 is 4 factorial. So this cancels to just 1. And so we have x to the 0 plus 2 to the 4th is 16. Or x to the 4th plus 8x cubed plus 24x squared plus 32x. Whoops, this shouldn't be plus here, this should be times. Plus x to the 0 is 1, 16. So if we go back to our expansion we did before, notice our coefficients now match up. There's the 1, there's the 4, there's the 6, there's the 4, there's the 1. X to the 0 is 1. And then 16 matches 16, 8 matches 8, 4 matches 4, 2 matches 2, and 1 matches 1. And our final answer here, comparing these two, exactly the same. So Pascal's triangle is great to give us this pattern, 1, 4, 6, 4, 1. What it doesn't do is give us the other terms. The binomial theorem says I can take Pascal's triangle into account, make sure that I satisfy that pattern, 1, 4, 6, 4, 1. But I will also tell you exactly what power of x, and in this case 2, or what exactly power of a and b you need to have. So this is very useful when you're expanding binomials. So I have a practice for you to try. Expand 3 to the m minus n to the 4th. So I'd like you to pause the video and try here, but before you pause, I just want to make sure that we're all working from the same place. There is a minus here. So the general form is a plus b to the n. That means the a is 3m here, and the b is negative n, because it should be a plus. And of course, our n equals 4. Now, don't get these confused. I just happen to use that term. So pause the video here and expand this out according to the binomial theorem. And I will give you the answer here in a second. Okay, so let's go through this. So when you expand it all out, you should have 3m to the 4th in parentheses plus 4 over 1 factorial times 3m in parentheses cubed times negative n to the 1st plus 4 times 3 over 2 factorial times 3m squared times negative n squared plus 4 times 3 times 2 over 3 factorial times 3m to the 1st times negative n cubed plus 4 factorial over 4 factorial times 3m to the 0 times negative n to the 4th. And when you expand this out, you end up with 81 m to the 4th minus 108 m cubed n plus 54 m squared n squared minus 12 mn cubed plus n to the 4th. So that is using the binomial theorem. It just takes some practice. If you didn't quite get this answer, try it again. Make sure you're setting up all of your terms correctly according to that theorem. And then make sure that you're simplifying correctly. And you can, the nice thing is you can practice these over and over again because you know what it's supposed to look like. You know how it's supposed to end. So the last thing we want to take a look at in this section is finding a specific term. So how to find the nth term of a binomial expansion. So if we want to know a specific term, so if we have a plus b to the n, then the r plus 1th term is always n factorial over r factorial times n minus r factorial times a to the n minus r times b to the r. Now this does mean we have to jump through one little hoop. If I want to know what the 6th term is, my formula gives me the 7th term. So I have to make sure that I'm finding the right r. So let's look at an example of how we would handle that. So find the 8th term in the binomial expansion of 2x minus y to the 10th. So this is really common. Sometimes we just want a specific term and we have a big expansion. We don't necessarily want to expand out to the 10th power. Even though we have the binomial theorem and we could do it, it's just going to be tedious. Right? We have to write out all 10 terms, simplify all 10 terms, make sure we don't make any errors. With this formula, we can just pluck out the 8th term without having to do that. So I said we had to jump through a hoop. Our formula is for the r plus 1th term. So if we want the 8th term, we just set 8 equal to r plus 1. Well, that means r equals 7 for our formula. So now we identify our pieces. Our n is 10, right? Our a is 2x, and our b is negative y. Remember, the general formula is supposed to be plus. So since we have a minus, that minus gets included in the b. So now our formula says 10 factorial over 7 factorial times 10 minus 7 factorial times 2x to the 10 minus 7 times negative y to the 7th. And then we simplify. So 10 factorial, we're going to expand out to 10 times 9 times 8 times 7 factorial over 7 factorial times 3 factorial. Cancel, cancel. This is 2x to the 3rd, and this is negative y to the 7th. So we actually did this earlier. 3 factorial will cancel into the 3, leaving a 3, and into the 8, leaving a 4. So this will be 120 times 2 cubed x cubed times negative y to the 7th, because any negative raised to an odd power is negative. And so our final answer then is 8 times 120 times a negative 1, which is negative 960 x cubed y to the 7th. So you can kind of see how much work there was for just this one term. Now imagine doing that 9 other times, because you're going to have 10 terms in total if you were to expand this. So this way, with this formula here, we don't have to do an expansion every time if we're just looking for a specific term. So that is the end of Chapter 4, Section 14.5. We have 2 sections left to go in the class.